Hey guys, Mr. Smith here, and we're doing a video lesson for Unit 6, Lesson 2. We're going to be talking about logarithms today. Um, my In the top right there, the little screen capture of me, it's really big, and I'm not sure how to make it smaller today. I can't resize it. Can I resize it? I can resize it a bit. It's still pretty small, but it is what it is. So we're talking about logarithms. Let's get started. So where we kind of left off in our last lesson is we reviewed exponential functions, reviewed their properties like y-intercept is 0, 1, horizontal asymptote y equals 0. We looked at a new property that the instantaneous rate of change is always proportional to the value of the function. But then we looked at its inverse, and we saw that the inverse is a function, right? We have it graphed, the diagram at the right there. It's a function, passes vertical line test. But what we don't know is how can we describe that function? If y equals b to the x is an exponential function, the inverse is just swapping x and y, x equals b to the y. But how can you write that, with the y by itself, like y equals? The introduction here mentions maybe you have a population that's growing. I'll just make up an initial population of 100, and let's say it's doubling every hour or something. How would you write that? Like, what if you wanted to get the time as a function of the population? How would you rearrange that equation for t? So we're starting to develop those skills today. The way we do that is by using something called logarithms. So as we mentioned, normally we like to express the y coordinate in terms of the x coordinate. So when we have x equals b to the power of y, we're going to restate it in words first and then how it can be written. So x equals b to the power of y, we're going to say that y is a logarithm. And I should tell you guys, I'm writing in my classroom where I taught my last class, and it's during lunchtime. So somebody might pop in and say hi, or we'll just deal with it. Y is the logarithm of x to the base b. In math, we write it this way. If x equals b to the power of y, then we say y equals the logarithm base b of x. And as you can see, that's the equation of the inverse. We need to get comfortable with logarithms and get used to this new idea of kind of rewriting an exponential expression in terms of logarithms. Let's continue. So let's do a couple examples. So here I have three exponential relationships. We're going to write them in this new log notation. So 2 to the power of 3 is equal to 8. So what's the base? The base here is 2, right? So we're going to write this as log base 2 of 8 is equal to 3. So if you, I know you guys have this on your page, so I'm just going to write it here. X equals b to the power of y. We can rewrite that as y equals log base b of x. And you can see the base stays the same. The kind of result of this power goes in the argument of log, and then the exponent is what it all equals to. Another way of saying this, log base 2 of 8 just means this. It's like 2 to what exponent? gives you 8. And of course, we know the answer is 3, right? So log base 2 of 8 equals 3. So that's another way of thinking about logs. So rewriting 5 squared equals 25. I'm going to erase the base I have there, just so I have some room to write. 5 squared equals 25. We write that as log. The base is 5, 25. So this is saying log base 5 of 25 is saying 5 to what exponent gives you 25? Well, we know that's equal to 2. So we have this relationship of how exponential form and log form are related. Getting a few examples here. Let's do another one. What's the base? The base here is r. R to the power of s equals t. So log base r of t. R to what exponent gives you t? In our expression here, it's s. This is the definition that really helped me as I was learning these in high school. It's just thinking about, the base of 2, it's 2 to what exponent gives you 8. So here's another example. Maybe just on the fly, copy this down in the margin, but just have a think on this one. How about log? Evidently log does not have an O in it. Yeah, this is just improvising. This isn't part of your note. How about log base 4 of 16? What's that equal to? You can pause the video and take as much time as you need. Remember what that's asking. The base is 4. 4 to what power gives you 16? It's 2, because 4 squared equals 16. How about this one? Log base 10 of 1,000. What's that equal to? Again, pause the video, have a think on that. Remember what this is asked. This is saying it's asking 10 to what power gives you 1,000? It's 3, because 10 to the power of 3 is equal to 1,000. Definitely takes a bit of getting used to. We'll do a lot more examples as we proceed through it today. Let's continue. All right. So we've talked about the logarithm function. Let's get it defined here. The logarithm function is defined as y equals log base b of x. We know it's a function because we've graphed it's the inverse of b to the power of x, and we saw it's a function. It passes vertical line tests. So it is a function. In words, we would say, or y equals the logarithm of x to the base b. I'll tell you how I read that. Just that kind of doesn't roll off the tongue for me. I like to say log base b of x. That just rolls off the tongue a little bit better for me. Now, a couple things. This is only defined because remember the way that we set up this definition for logarithm is it's the inverse of the exponential function b to the power of x. For that function b to the power of x, we required b to be greater than 0. Either we had exponential growth for b bigger than 1 or decay for b being between 0 and 1, but it had to be bigger than 0. So this is only defined for a base being bigger than 0, and also the base can't be 1. Why can't the base be 1? Well, I'll maybe flip back a couple of slides, and please, you do not need to copy this down. But what if you had an exponential function where the base was 1? What would that graph look like? Well, that graph would look like a horizontal line. 1 to the power of x is just equal to 1. And your function would look like this, which isn't exactly bad. But when you try to take the inverse of the function y equals 1, you get a vertical line at x equals 1. That's not a function. It doesn't pass a vertical line test. So that's why we say that the b has to be greater than 0, but b can't be 1. because in that one case, if b is 1, you don't get a function. You get a vertical line like I've showed you guys here. All right. As I've mentioned, back to my pen here, the logarithm y, it's the exponent to which the base must be raised to give a value of x. So let's look at like maybe one more example of that here. Let's do, how about log base 2 of 32. What is this saying? This is saying 2 to what power gives you 32? 2 to the power of 5 equals 32. So any function, y equals b to the x, we can write it in log form, just like we've been doing. We have an example over here. Just one more example. I know we've done a lot. Here's a power expression. 16 is 2 to the power of 4. That means 4 equals log base 2 of 16. And this one I did here, log base 2, 32 equals 5. That just means 2 to the power of 5 equals 32. When you get to your practice, you're going to see a lot of questions like rewrite in this form, rewrite in this form, just because it takes a bit of getting used to. It's a brand new idea, this idea of logarithms. Let's get a bit of practice doing that. So here are 3 expressions in exponential form. I want you guys to rewrite them in log form. There's not really a lot of work to show. You're just going to be rewriting these guys. So if you want to pause the video and give that a try, you can unpause when you're ready. I'm going to dive right in here. Hopefully you've given them a try. So the exponent here is 4. The base is 2. And we're doing the logarithm of 16, base 2. Again, 2 to what exponent gives you 16? It's 4. In our next example, m equals n to the power of 3. The exponent is 3. The base is n. We're doing the logarithm of m. That m has an extra that m has an extra thing on it. Log base n of m. That's better. Right. And for c, I might start with the right-hand side. The base is 3. Log base 3 of 1 over 9. 3 to what exponent gives you 1 over 9? Well, 3 to the power of negative 2 gives you 1 over 9. So negative 2. All right. And so please, when it comes to practice, do each one of these that you can just to get more experience converting to log form. All right, let's continue. Worth noting, you can get negative results when you do a logarithm. That's okay. And as we talked about, that base is always bigger than 0, but can't be 0 or 1. And I can just show you the graph. If we look at the graph of log, you can see that the graph of log is sometimes negative, and that's okay. All right, continue. Let's evaluate some logarithms. We've got some experience going back and forth. Let's actually evaluate some logarithms. And you're going to hear me kind of repeat the same phrase over and over again, like for part A here. Log base 3 of 81. So again, we have to ask ourselves, 3 to what exponent gives you 81? Many of you guys can probably just see the result there. I'm going to show you a way that you can kind of show your work in order to visualize this. So for A, let's say we don't know what log 3 of 81 is. Let's set y equal log base 3 of 81. You can rewrite this in exponential form. The base is 3. The exponent is y. The result, 81. 3 to the power of y equals 81. This is just mathematically kind of framing what I described earlier. 3 to what power gives you 81? Well, we know 81 is 3 to the power of 4. And so we can see, okay, y is equal to 4. So log base 3 of 81 is equal to 4. Let's try B. So again, log base 2 of 1 over 8 is asking 2 to what power gives us 1 over 8. If we're unsure about that, let's set it up. Y equal log base 2 of 1 over 8 means 2 to the power of y gives us 1 over 8. We can write 1 over 8 as a power of 2. This does require you to kind of have a rudimentary knowledge of your basic powers of 2 and a little bit of negative exponents. But 1 over 8, we know 8 is 2 cubed. 1 over 8 is 2 to the power of minus 3. Minus 3. So log base 2 of 1 over 8 is equal to minus 3. We've got it. Let's squeeze in C here. 10 to what exponent gives us 0.01? So let's let y equal log base 10 of 0.01. So that's asking 10 to what exponent gives you 0.01. Maybe you might find it helpful to rewrite 0.01 as 1 over 100 because that makes it a bit more clear what power of 10 that is. 10 to the power of y that's 10 to the power of negative 2. So y equals negative 2. Log base 10 of 0.01 is equal to negative 2. We got it. So when you're evaluating logs, it's all about thinking, okay, my base to what exponent gives you my argument here. And so we've done 3 examples of that, how to set those up. Let's continue. There's an interesting property that we're going to look at a little bit later. And it's the following. If I have the log of some base a to some power b, what is this equal to? Well, think about what that is saying. What that is saying is my base a to some power gives me a to the power of b. Well, that would just be equal to b. A to the power of b gives me a to the power of b. And so we can think about that, maybe reframing one of our problems. Let's relook at log base 3 of 81. I can rewrite that like this. That equals to log base 3 of 3 to the power of 4. And now this is asking 3 to what exponent gives me 3 to the power of 4? Well, it's just equal to 4. So that can be a helpful property. We'll definitely be coming back to that property in a bit. Now, in a lot of applications, it is common to use a base of 10. And so what we call logarithms that use a base of 10, we call those common logarithms. And when you write a common logarithm, it's not necessary to write the base. So there actually is, in calculus, you'll learn of a second common logarithm. In our course, the only one we'll be using is base 10. So when we're using base 10, we don't write the base. So instead of writing log base 10 of 100 equals 2, and again, we know that means that's 10 squared because it's 100. We know how to interpret that. We don't write the base 10. You just write log 100 equals 2. So if you guys are doing problems or come across anything and you just see log with no base, you just automatically connect the dots. It's log base 10. We've done some exponential form to logarithm form. Can you guys take these and rewrite them in exponential form? So if you'd like to pause the video and give that a try, not a lot of crazy work to show. Can you write these in exponential form? I'm going to continue now, assuming you've paused the video and gave that a try, hopefully. I might actually leave myself some more room just to label a few things. Big thing is that the base is always the base. 4 here is the base. The result of doing a log gives you an exponent. Remember, this is asking log 4 is 64, is saying 4 to what exponent gives you 64? That exponent is 3. 4 to the power of 3 equals 64. For b, what's the base? Don't see one. That's because it's written in our common logarithm form. The base is 10, right? We just don't write it. The base is 10. The exponent would be y. So we can write b, we can write that as 10 to the power of y gives us x. And again, guys, when you get to your practice, do as many of these as you can just to let that kind of sink home, going back and forth. It's going to be really useful for us in a little bit when we start solving some equations where the variable's in the exponent. All right. The last thing we're going to do is approximate some logarithms. So going back to example 2, all of these logarithms we could work out exactly because 81 is a power of 3. 1 over 8 is a power of 2. 1/100th or 0.01 is a power of 10. But going to example 4 here, 10 is not a power of 2, right? Like 2 cubed is 8 and 2 to the power of 4 is 16. Somewhere between 3 and 4, we don't exactly know what it is yet, like 2 to like maybe 3.2 or something like that, is going to give us 10. So we're asking in A, 2 to what exponent gives us 10? We're going to solve A by using systematic trial and error. And keep in mind, later on, we are going to move away from trial and error, and we'll have a process for doing this on our calculators. Part B, we're not going to use systematic trial and error. We're going to be smart about it. We're going to use technology. You know what? Maybe even after we do part A by hand, we'll bring it up in Desmos as well. Okay. So let's start with part A. What's our starting point? Well, I mean, our starting point could be this. We know that log base 2 of 8 is equal to 3. And we know that log base 2 of 16 is equal to 4. So log base 2 of 10 has to be somewhere in the middle. So log base 2 of 10 is between 3 and 4. That's our starting point. So let's just get started here. So our first estimate makes sense if it's between 3 and 4, why don't we try 3.5? And then just check. What's 2 to the power of 3.5? Let's see how close we get. My calculator tucked away here. Let's bring it back out. 2 to the power of 3.5. 11.3, we can do better. So 11.3, too high. Let's try something lower. Let's try 3.2 maybe. And we'll try 2 to the power of 3.2. Does that give us close to 10? 2 to the power of 3.2. Okay, I got about 9.19. Too low. Okay, let's take it up a notch and let's try 3.3. 3.3. 2 to the power of 3.3. Okay, we're getting closer. That's 9.85. It's decent enough, 3.3. But let's see if we can get any better. Let's go to a couple of, I'll just say like getting close. Let's tick it up a little bit. Let's try 3.31. See if that gets us there. 2 to the power of 3.31. 9.92. Maybe 3.32 is good. I got a feeling that it is going to be. to the power of 3.32. 9.99. Okay, I'm going to call that good enough. Seems good. So systematic trial and error, just try something. If it's too high, then drop it down. If it's too low, bump it up, and keep refining and refining until you get close. And so I think we can comfortably say for part A that the log base 2 of 10 equals approximately 3.32. So let's bring up Desmos and do a little verification. And again, guys, keep in mind, like we're going to show you guys how to do that on a calculator. We just got to start somewhere. I want to keep these. Desmos, here we go. I need to get my face out of the way. Get out of the way, face. All right. And that is way too big. All right. What we're going to do is face go down there. We're looking for 2 to what power gives us 10. So we're going to look at the graph of y equals 2 to the power of x. Okay, there it is. There are several ways to, my face can never just be in the right spot. Several ways to go about this. My preference to make Desmos actually just show you where it is to add a second function. And we're looking for, remember, we're looking for log base 2 of 10 means 2 to what power gives you 10. So we're trying to find when 2 to the power of x is equal to 10. So let's just graph the second function, y equals 10. And let's graph that. And then Desmos actually just gives you the point of intersection, 3.32. So we did pretty good. We got 3.32. If we had maybe tried 3.3211 or 3.321, 3.332, we can get even closer. But 3.32 seems pretty good. Let's head back to the PowerPoint, and we'll just set this problem up and then head to Desmos and solve it. So let's do part B. So in part B, we have log 2500. And I might say just like, actually, I might just rephrase that. I'm going to use a technique from earlier on. I might just say let's use x this time. I might just say let x equal log 2500. And what does this mean, right? It means, so remember log 2500, that common logarithm, the base is 10. This means 10 to the power of x equals 2500. 10 to what power gives us 2500? Now we can use guess and check. 10 to the power of 3 is 1,000. To the power of 4 is 10,000. That's a pretty broad range in between. Systematic trial and error seems a little like not a good use of our time. So let's head to Desmos. And we're doing 10 to the power of x this time. And that's going to be equal to 2,500. Now I'm going to change the scale on our graph a little bit. Get out of the way, face. I think maybe I'll make this like minus 500. Make this 2,500. Maybe a bit more, maybe like 2,800 just for me to see. All right. There we go. We have our graph of 10 to the power of x. We've graphed 2,500. When are they equal? And we can see to 3 decimal places, about 3.398. 3.398. I'll just say Desmos x equals approximately 3.398. And just as a check, try it yourself. Do 10 on your calculator to the power of 3.398. I'm going to do it too. It should give us, well, one, it passes the eye test. It's between 3 and 4. But let's just do it. 3.398. 2500.35. It's a pretty good estimate. So I think we did okay. So log 2500, about 3.398. Now I will say, we don't have the skills to do yet. We're going to show you that in our next lesson, I believe. But log 2500, if you guys have a look at your calculators, you actually have a log button. You have a button for that common logarithm. Mine is right there. And you can actually just try this for yourself and put in log 2500. Log 2500. And we get 3.398. Yeah, so pretty cool. All right, so in our next lesson, we're going to look at more detail at just the graph of the log function. It's a brand new function. It's got some interesting properties. For example, it doesn't have a y-intercept. In fact, it has a vertical asymptote that you only approach from the left. It cannot be negative, or you cannot have negative x values in the domain. It has an x-intercept but no y-intercept. So we want to get comfortable more with the graph so we can do some modeling. And we're going to do all the transformations we've been applying to power functions, polynomial functions, trigonometric functions. We're going to apply to logarithmic functions as well. That's for next time. In the meantime, I do have some suggested practice for you guys. Just lots of rewriting from exponential form to log form, lots of evaluating logs, using technology to evaluate a few logs. But please do as much as you need to get really comfortable with this new idea of logarithms. That's it from me for now, guys. Hope you're having a great day. Stay well, and we'll see you soon.